Hello everyone, and welcome back to our physics lecture series. Today, we're exploring a classic thermodynamics problem that beautifully illustrates the first law of thermodynamics. This fundamental law is crucial for understanding energy transfer in systems ranging from car engines to atmospheric processes. Let's begin by visualizing our setup. Imagine a cylinder containing gas, sealed by a movable piston. Heat is supplied to this gas, causing it to expand and push the piston upwards. Now, let's identify our key variables. Q, the heat supplied to the gas. We're given Q equals 500 joules. By convention, heat added to the system is positive, so Q equals plus 500 joules. W, the work done by the gas. The problem states the gas does 200 joules of work as it expands. Work done by the system is positive, so W equals plus 200 joules. Delta U, the change in the internal energy of the gas, which is what we need to find. This represents the total energy contained within the gas. The core principle here is the first law of thermodynamics. This law is essentially a statement of energy conservation for thermodynamic systems. It states that the change in a system's internal energy, delta U, equals the heat added to it, Q, minus the work done by it, W. So our essential equation is delta U equals Q minus W. Now, let's substitute our known values. Q equals plus 500 joules and W equals plus 200 joules. Delta U equals plus 500 joules minus plus 200 joules. This gives us delta U equals 300 joules. Let's quickly check our answer. The units are joules, which is correct for energy. The positive sign means the internal energy of the gas increased. This makes sense. 500 joules were supplied as heat, 200 joules were used for work, so the remaining 300 joules must have increased the gas's internal energy, perfectly aligning with energy conservation. So the change in the internal energy of the gas is 300 joules. This increase would typically correspond to a temperature rise. Understanding this principle is vital for designing engines, refrigerators, and even for studying atmospheric dynamics, where energy transformations are constant. A key insight is the crucial role of sign conventions. Always be mindful of whether heat is entering or leaving, or if work is done by or on the system. This directly impacts your calculations. In summary, the first law of thermodynamics, delta U equals Q minus W, is a powerful expression of energy conservation. It illustrates how energy transforms between heat, work, and internal energy, but the total amount remains conserved. This fundamental principle connects microscopic energy states to macroscopic interactions. Thank you for joining me today. If this explanation was helpful, please like this video, subscribe for more physics and math insights, and share it. Feel free to leave questions or comments below. And a special note, if you have a problem you'd like solved, you can support the channel by donating. Each month, we'll select a few donor-requested problems for dedicated videos.